put it in the group chat there. Yeah, the Zoom group chat, and I'll answer it, not necessarily at the same time that you ask it, but when we get to like a checkpoint in this presentation, okay? So let's just continue to wait for people to join. I'll start at like 6:01 because that seems fairer. There was a question which I'll answer now because there's time. Someone asked if this is useful for Edexcel, this presentation. Now, actually, I did Edexcel myself. So, uh, yeah, this is really actually going to be useful for Edexcel too, as well as AQA and OCR. I looked at all the specs when making this presentation, so everything should be covered. Yeah, but definitely useful for Edexcel too. Although I haven't included Edexcel specific questions, like past paper questions, but it should still be useful because like it's effectively the same for every syllabus, and the questions are effectively the same as well. All right, let's just wait a bit longer. Okay, let's make a start then. It's 6:01. Some people might still join, but we're not going to get into the deep stuff for a couple of minutes anyway. But as I said, to those of you who were there a couple of minutes ago, my name is Scott, and we're going to go through redox chemistry today. So that includes three major areas. We're going to look firstly at AS redox chemistry, so looking at redox equations. Then we're going to look at redox titrations, and then we're going to end with electrodes and like the electrochemistry and all of that basically. And as I said before, if you have any questions during this presentation, please don't hesitate to put it in the chat, and I'll answer it when it's relevant and when there's time. But yeah, let's just make a start by looking at some of the specs. So I haven't included Edexcel in here, but as someone asked before, this is still relevant to Edexcel because the specs really overlap on this topic. We're going to start by looking at AS redox chemistry. This shouldn't take too long to go through because it's fairly basic. There's not actually that much to it. But what we want to do is we basically want to consider what oxidation states are, what the definitions of reduction and oxidation are, and then also how to balance redox half equations and redox equations. Yeah, we are going to cover batteries and EMFs, by the way. Someone asked that in the chat. That's in electrochemistry, so that's like the final third of this presentation. But let's make a start on the AS level stuff. So we're going to start by looking at the definition of redox. Now, this is one of the most important things in the entire A level for you to really get your head around. But essentially, when chemical reactions occur, there are different ways they can occur. And one of the ways they can occur is that electrons are transferred from one species to another species. So one atom can give an electron to another atom, and that will form ions, for example. Let's look a bit more in depth at this though. So the process of electron gain, a species that gains electrons is referred to as reduced. And if it loses electrons, it's referred to as oxidized. There's a couple more important things to consider. Now, this isn't always true because not every chemical reaction involves oxygen. But if a species, an atom, or like something else, like a molecule, gains oxygen, that's oxidation. That it's literally in the word oxidation, gains oxygen. And if it loses oxygen, it's reduction. So you're starting to see that these are inverse terms. They mean exactly the opposite. I've included hydrogen as well here because this is a bit more advanced than the other two. But when you're looking at organic chemistry and redox reactions there, it can be a helpful way of considering what's been reduced and what's been oxidized is by looking at hydrogens. So it's the opposite of oxygen, basically. A species that gains hydrogens can be referred to as reduced, and a species that loses hydrogens can be referred to as oxidized. And I've included an example of this here. So ethanol to ethanal to ethanoic acid, you can see that this is oxidation, and that as you successively go along, you're losing hydrogens. And then this concept of oxidation number we'll look at on the next slide, I think. But if the oxidation number becomes more negative, you're reducing it, so it's reduction. And if it becomes more positive, you're oxidizing it. So that's oxidation. How can you remember this? Well, there's a couple of ways. This is the most famous way, is oil rig. Oxidation is loss, reduction is gain, and this refers to electrons and also hydrogen. And then you can just remember that the word oxidation implies the gain of oxygen. So there you go. That's how you can remember. A couple more definitions to go through here. This one's quite confusing. The concept of reducing and oxidizing agents. The way to remember this is that a species that is reduced is the oxidizing agent, and a species that is oxidized is the reducing agent. So it's literally the opposite. And if we look at this example here of the iron and chlorine reaction, we can see that iron is oxidized. It loses an electron. Each ion loses an electron. So iron is oxidized, and chlorine, contrastingly, is reduced. But because iron is oxidized, it serves as a reducing agent for chlorine. It causes chlorine to gain electrons and become reduced. So yeah, that's the way to look at it. Quite a confusing concept, but just think that the iron has essentially transferred electrons to chlorines. The electrons are going from here to here, and so the iron is oxidized, but in doing so, reduces the chlorine. Okay, this is another definition, disproportionation. Just a definition to remember, an element in a single species is simultaneously oxidized and reduced. And we'll look at an example question later on that just really highlights what this means. Next slide. Okay, so when I talked about oxidation states earlier, there are just a couple of rules to define what oxidation state a species is in. So these, the way to go about this isn't just memorize them, it's to just sort of understand why they make sense. But basically, a single like species element inside an ion, so like Na plus, that's just sodium by itself, it has an oxidation state corresponding to the charge of the ion. So Na plus has an oxidation state of 1. If we look at a couple of these other rules down here, so like 3 and 4, oxygen always has an oxidation state of 2 minus. Remember that, except there's just a couple of exceptions that never really come up, but peroxides are like, it's an oxygen molecule like O2, but 2 minus. So each atom has a 1 minus oxidation state, but that's a really rare thing, so don't really worry about that. Usually oxygen is going to have a 2 minus oxidation state. Likewise, hydrogen is almost always going to have a +1 oxidation state. The exception is in some chemicals called hydride, so like sodium hydride, NaH, where it will have a -1 oxidation state. Fluorine, always -1. And if you want to understand why this is, look at the electronegativity index. The most electronegative species, so fluorine, they always are the more negative. They're always the more negative one. They're the strongest. They're the most likely to be to gain electrons and be reduced. So most powerful oxidizing agents is what I'm trying to say there. So that's why it works out like that. Pure elements like Ag, silver, it's just 0 is the oxidation state. And Roman numerals, so if you see like Fe and then Roman numeral 3, that just tells you that the ion has a 3+ oxidation state. If it's Fe2, it's a 2+ oxidation state. Couple of interesting, more difficult things to consider now. But if like a manganate ion, so I'm talking about MnO4 minus, the way they would denote that if they didn't write out the ion is they would say manganate and then Roman numerals for 7. So VII, 7 Roman numerals. That 7 in Roman numerals is referring to the manganese in that species, which makes sense if you think about it, because The manganate ion is MnO4, and then it's all got a 1 minus charge. If we think about oxygen, all four of those oxygens have a -2 oxidation state. So the oxygens are creating a total of -8. But the whole ion complex has a charge of -1, which means that the manganese must have itself a +7 oxidation state. So I'm just going to draw that out actually, just to really emphasize this. So this is a manganate ion, and if they didn't write it like that, they'd write it like this. So manganate VII. And what I'm saying here is that if you look at each oxygen, as I said, this isn't a peroxide, so each oxygen has a -2 oxidation state. The oxygens in this species have a -2 oxidation state. So that's a total of -8 because you have four of them. So, and the total of the oxidation states need to equal the total charge of that whole species. So -8 plus something goes to -1, it's +7. And that's what the Roman numerals are referring to there. And it's the same with sulfate. So the oxygens are -8 total, but you need to have an oxidation state of +6 for the sulfur in order to equal the -2 total. Okay, let's move on then. Um, the order, just to say this, the order of this is just arbitrary. They're not really any there's not really any order to these rules. They're just some rules to bear in mind when you're working out oxidation states. Uh, anyway, let's look at equations now. So this ordering is more important. You don't necessarily have to stick to this, but this is the easiest way to do it. Let's look at the examples when we're going through this. So you want to basically write an equation that shows you, I'm going to draw this out here, that shows you the conversion of MnO4 minus to Mn2 plus, okay? So this is basically, you know that in this reaction, manganate 7 gets reduced to manganese 2 plus. This is year 12 content, someone just asked in the group chat, but we're going to get into the year 13 after. This is just the foundations that we need to look at first. So the first thing we want to do is we want to balance the species. So that means just making sure that there's the same number of manganese on either side. So one manganese here, one manganese here. Then we want to balance we want to balance oxygens using waters. So if we look at below, the way they've done this is they've added 4 waters to the right-hand side. So now you have 4 oxygens on the right-hand side and 4 on the left-hand side. So oxygen's balanced now. But now we have a hydrogen imbalance. We have 8 hydrogens on the right and none on the left. So we need to add 8 hydrogens in here. So now it's all balanced. Manganese, there's one on this side, one on this side. Hydrogens, there's 8 and 8. Oxygens, there's 4 and 4. This is the top equation. But the charges aren't balanced. Ignoring the electrons there, the 5 electrons, the right-hand side would have a 2 plus charge, and the left-hand side would have a 7 plus charge. Therefore, in order to balance the charges on both sides, we need to add 5 electrons. We do the same for the upper equation, and you can see it ends up like this. And then the final step is treating them like simultaneous equations. So that's just making them have equal electrons. So we times the top one by 2 to get 10 electrons. So that would be 10. That would be 2 manganates plus 16 hydrogen protons plus 10 electrons goes to 2 manganeses and 8 waters. We times that by 2, and we times the bottom one by 5. And now they have an equal number of electrons and they balance, and we just combine them like this at the bottom. So that's how you do redox equations. And that's the end of the AS level stuff. Just a couple of questions to test your understanding of this. You don't need to write the answer, just maybe think about it in your head for a minute or so while I answer any questions. Yeah, so just read those questions and have an answer. The left one is OCR, the right one's AQA, but you can have a look at both. They could both occur in either exam board or in Edexcel. Okay, just because we're a bit pressured for time because there's quite a lot to go through, I'm just going to talk through how you would do this. The one on the left, OCR, the way to go about doing this is firstly define what disproportionation is. I noticed someone asked what that was in the group chat. A disproportionation reaction is when an element in a single species is simultaneously oxidized and reduced. So in this example, iodine, the element in a single I2 species, is simultaneously oxidized and reduced. So the way we prove this is that I2, iodine, has a zero oxidation state. HI, iodine, has a -1 oxidation state. And then HIO, the iodine would have a +1 oxidation state. So it's gone from 0 to -1, which is reduction, but simultaneously it's gone from 0 to +1, which is oxidation. So that's how you would go about answering that. And you have to include the oxidation numbers there. Okay, let's just read the group chat quickly. Yeah, so yeah, next one. Let's look at AQA now. Term oxidizing agent. Remember, I said it's quite confusing. An oxidizing agent is a species that is reduced, and in doing so, oxidizes something else. So it's by being reduced, it's gained electrons. Um, and then the half equations, I'm going to show you on the next page when we look at the mark schemes, but essentially balance the species like chromium and sulfur, balance the oxygens with water, balance the protons, balance the electrons, and then combine by simultaneous equation methods. So here we go. As I said, that's what it said, disproportionation, oxidation, reduction at the same time. And then you include the oxidation states. Remember, oxidation is an increase, more positive, going to a more positive oxidation state. Reduction is going to a more negative one. Oxidizing agent is an electron acceptor. It's been reduced. And then, as you can see, they've combined everything here. So if we look at the dichromate one, actually, this is just what I mean about balancing the chromiums. Cr2O7 2- has two chromiums in that species, and it's going to Cr3 plus. So the first step before we do anything is we need to balance the chromiums, and we do that by putting a big 2 in front of Cr3 plus. And then after that, we balance out the 7 oxygens by adding 7 waters. That gives us 14 hydrogen protons over here. And then last step, balance out the charges with electrons. And then combine it with by the one, and then multiply this top sulfur equation by 3. And now you have 6 electrons in this one, 6 electrons in this one, and combine them. Just to say, the examples I've used, you don't actually need to know them off by heart. You just basically need to be able to work them out. So like when I looked at the hydrogen peroxide manganate reaction, as someone's asking, don't know that off by heart, but just make sure you can work out how you would do that. Um, let me just see if anyone else is asking anything. Okay, let's move on. So now we're going to look at A2 redox chemistry, and this is in two parts. The first part, we're going to look at redox titrations, quite a tricky area, and then we're also going to look at another tricky area, which is electrochemistry, so how fuel cells and chemical cells work. And here's the spec for reference. Uh, and yeah, so this is OCR on the right, AQA on the left, and they're effectively the same. Edexcel is effectively the same too. Um, so someone's asked in the chat, and we're going to come to this literally on the next slide, but what's the color change for manganate to Mn2 plus? Uh, this is a very important color change. Strictly speaking, manganate, so if you have potassium manganate 7, that's going to be purple, and Mn2 plus is colorless. But as someone's saying, the pale pink, that if you're doing a redox titration, it's actually going to go to pale pink because the purple is so diluted. Your goal isn't to get it to a dark purple. Your goal is to literally just add a drop of excess manganate to that solution to create a pale pink color. And if that sounds confusing, I'm going to go into a bit more depth on this on the next slide. So a redox titration is the same principle as a normal acid-base titration. what you're doing is you're using a chemical in a burette that you know the concentration of. So you would know how concentrated the potassium permanganate is, and you're adding it to a different chemical in a conical flask um, until you get the color change. Um, Color change for this reaction, just to go through this one more time. The potassium permanganate in the burette is purple. Any manganese Mn2 plus that forms is colorless. However, the goal of your titration is to add just enough manganate to completely react with the iron over here. And that means that you'd literally be adding a tiny, tiny, tiny drop of excess manganate to a colorless solution. So instead of being a deep, dark purple like you see in the burette, the color change you would say is colorless to pale pink. So it's quite a tricky thing to get your head around. But in an exam, if they ask what the color change is for this titration, colorless to pale pink, even though the real potassium manganate 7 is purple. And that's just because it's so diluted in this titration method. Um, just to clarify about this ion, the MnO4 minus, there's different names for it. I'm referring to it here as MnO4 minus. It's also called permanganate, and it's also called manganate 7. So there's just the different ways to describe that. So there's, strictly speaking, on your specs, there's only two redox titrations you need to know, this one and the iodine-thiosulfate one, although you could be asked about other ones, but it would be applied as opposed to memorizing stuff for the exam. So this is one to know. Let's talk about how this works though. So you're adding a known volume of a known concentration of potassium permanganate to a conical flask to exactly react with iron 2 plus. So what we do then is we use N equals CV to work out the amount of moles of manganate 7 permanganate that have reacted. So N equals CV. That tells us the moles of manganate 7. Using this equation that we would have generated using the AS knowledge on the previous few slides, we can use this equation to work out the moles of iron that have reacted, because we know the stoichiometry, the big numbers, is 1 manganate 7 reacts with 5 iron 2 pluses. Therefore, let's say 1 mole of permanganate was used in this reaction. 5 moles of Fe2 plus must be used to exactly react with it. So now that's what the step is. First calculation we do, N equals CV, find how much permanganate we've used. Next step, convert that to the amount of iron we've used using the big numbers. So yeah, that gives you the amount of moles of Fe2 plus. A very important step now is that if you've prepared a standard solution, you need to multiply it up. So we did a titration on 25 centimeters cubed of Fe2 plus, but if we have a bigger flask and that was just a sample of it, we're gonna have to multiply up. So multiply our number of moles of Fe2 plus by 10. Next, we want to find the mass of iron. Mass equals Mr times moles. And then finally, the percentage mass of iron in the tablets, which would just be the mass of iron discovered on titration divided by the mass of the tablets multiplied by 100. So that's just how the maths of this works. Okay, let me just read through any questions. Okay. So that's just an experiment that you might have done before, which is your teacher tells you how much, find the percentage content of iron in some pills. And then you would just go about it by preparing a standard solution of that iron by mushing it up and adding acid to it. The reason you add the acid is to provide these protons over here. And then now that's what's in the flask is a mixture of Fe2 plus and acid. Do the redox titration and then do the calculations as there. Next slide. The next slide, don't worry, I know it's a lot of content. We're not going to go through all of this. It's just there for reference. but this is the iodine-thiosulfate titration. This is another one that you all need to know about, and it relies on the reaction between iodine and thiosulfate. So I'm just going to draw out this equation so it's just more clear for you. But I2 plus 2S2O3, so this is thiosulfate. Sorry if it's quite messy, goes to 2I minus plus S4O. Oh, that's bad. Quite messy there. Sorry. SO4, S4O6 2 minus. Okay. Sorry, I just got let me just okay. So this equation that I've done over here, which is over here on the PowerPoint where my cursor is, that's an equation that you really should try and learn off by heart. The reason being that it comes up a lot in organic chemistry. Let's look at this experiment now for the iodine-thiosulfate titration. So basically, you want to work out how much oxidizing agent you have in a sample. And the way you do that is you react it with some iodide, some potassium iodide, and you produce iodine. So that's the top equation over here. So the oxidizing agent that CGP have used here is potassium iodate, the IO3 minus, and you're using iodide to produce iodine so that you can work out how much potassium iodate you have. That sounds confusing, but I'll just explain it as we go along. So you've produced iodine now, and now you do the iodine-thiosulfate titration using this equation over here. Relies on exactly the same principles as the manganate one. But this time you have thiosulfate in the burette and iodine in the conical flask. And the color change will now be dark blue to colorless. The reason it's dark blue is we add starch to the iodine, because remember from like biology, the iodine and starch gives you dark blue. And then it turns colorless as all of the iodine is reacted and forms iodide, 2I minus. So the goal of this titration is to add exactly enough S2O3 minus to the iodine we have present, the unknown amount, to turn it from blue-black to colorless. Couple of notes about starch to include is that we want to add the starch near the end of the titration. If we add it at the start, it makes it like really messy and hard to fully dissolve, and it's just annoying. We also want the starch to be fresh so it actually works. Just to iterate here, I know what I drew was messy over here. Yeah, and you're right. There should actually be a 2 minus there. I was just trying to copy out out the equation here, but essentially this is this, okay? Where my cursor is. That is the iodine-thiosulfate titration. So now through the titration, we can use N equals CV, moles equals concentration times volume, to work out how much thiosulfate was reacted, okay? And using the big numbers, we know that 1 mole of iodine reacts with 2 moles of thiosulfate. Therefore, the number of moles of iodine formed in the first step of this reaction must be half of the number of moles of thiosulfate used in the redox titration. So now we can basically just work backwards. And yeah, we find the moles of iodine, and then we can use the first equation to find the moles of iodate, just working back with that. Don't worry if you're still a bit confused. We're going to go for a worked example in a minute where it should all make a lot more sense, because because you'll see how it really works. Okay, next slide. Just a couple, we're going to do a practice question now, but just a couple of tips before we do. When you're doing any maths question in chemistry, what you want to do is be very careful. Same with biology as well. A lot of people just rush the maths questions, but if you actually want to get the marks, you have to take your time over them and think. First thing is about significant figures. Usually there's nothing to worry about there. Just give everything to three significant figures. The exception is if it asks you for like, if it specifically mentions it. If it says give something to two significant figures, give it to two. Why would you give it to three if it says that? If it says give something to the appropriate number of significant figures, then you give it to the number of significant figures that the like least precise data is to. So if you have like a data that is like 0.51, that's two significant figures, and you therefore have to give your answer to two significant figures. But usually giving everything to 3SF is fine. They don't really care. There won't be marks for that. There are a few exceptions as well, as someone said in the chat. pH, always the two decimal places. Very important tip here, tip number 3. The way that a lot of people lose marks in a lot of the maths and chemistry questions is that they use the incorrect units. So this applies to every topic that uses maths. Think about energetics like entropy and Gibbs free energy. A lot of people don't switch between kilojoules and joules, something as simple as that, but it throws off all your calculations if you do that. So it's quite an annoying thing to do. In terms of redox titrations, be very careful about the use of centimeters cubed and decimeters cubed. Have a think about how many centimeters cubed are in a single decimeters cubed. The answer is 1,000. So just in case you didn't know that. So timesing and dividing by 1,000 is important. Someone in the chat asked about significant figures. If they give you a mix of data, so one piece of data is to 2SF, one's to 3, one's to 4, and they say give your answer to the appropriate number of significant figures, give it to 2, because that's your least precise data. But as I said, usually don't worry about them. 3SF is the simplest thing to do unless it specifically mentions them. Okay, let's have a look at the example now. This is taken from OCR, but if you're doing AQA, you can still have a look at it and try and think about how you'd go about solving this. You don't need to produce a specific answer, but just have an idea about how you would go about working this question out. I'll give you another 30 seconds to a minute or so. How many marks would this be? Someone asked. I'm pretty sure this was a 6 marker actually, because there's quite a lot to it. If not, if I'm wrong about that, it's at least 4. But if you got the wrong answer, don't worry about that. You can still get most of the marks. The answer itself only gives you 1 mark. So just about working, like the working gives you quite a few marks. Let's go through it now. A top tip again with maths in chemistry is to work backwards and start with what you know. So I'm just going to scan through this and I look at step 3, where we're doing the actual titration. And we can see that 12.60 centimeters cubed of potassium permanganate is used to reach endpoint. We know the volume of manganate 7 and permanganate, sorry, we know the volume of the permanganate and we know the concentration of permanganate. So if we know C and we know V, we can work out N. So therefore, I would work out the moles of permanganate, this over here. And now what we want to do is we want to work out the moles of the other thing we're trying to work out, the sulfur species. So we would just use the big numbers to do that. We divide the moles of permanganate by 2 and then by 5. and then times by 5 to give you the moles of SO3 2 minus that has been involved in the reaction, times by 10, because this is what I was saying earlier. This is only a 25 centimeter cube sample of a 250 centimeters cubed standard solution. So times the moles of SO3 2 minus by 10. And then you can work out the mass of sodium SO Na2SO3. So you can work out the mass of that. Very important thing as well is this particular question, and a lot of the others you see, there is a mark just for saying yes, it complies with the food safety regulation, or no, it doesn't comply. So whatever answer you get, whatever mathematical answer you get, always make sure to refer to what the question is asking, which is, does the burger comply with the food safety legislation? Let's have a look at what the mark scheme would say. So yeah, as I said, work backwards, find the moles of permanganate, find the moles of SO3 2 minus in 25 centimeters cubed, times by 10 to account for the whole big flask. And then find the mass equals MR times moles, remember that. Convert the mass for 1 kilogram of meat, and then you can basically say if it complies or not. So yeah, so that's you, as it says here, you have to say that it's less than the maximum permitted value. Okay. So that's the answer there, by the way, is 0.7566 grams. Anything in that ballpark is fine. Someone says they got 757, which yeah, is perfect because you did, as I said, 3 significant figures. They really don't care. Look at what it says here. Allow 3SF or more throughout. So yeah, that's perfect. By the way, another thing I need to mention is about significant figures. Don't round during your working, only round at the end of your answer. Because if you round too early, your answer is going to be inaccurate, not precise enough, because you're going to have rounding error. So keep every number on your calculator until the very end. Let's move on now to electrochemistry. Oh, before I do that, actually, someone just asked, where did 1,000 divided by 525 come from? Okay. So the reason we do that step is because if you look at the question, this researcher is using 525 grams of burger meat, okay? So all of the SO3 2 minus comes from this 525 grams of burger meat. But the food safety legislation talks about the sodium sulfite per kilogram of burger meat, okay? So we basically need to work out per kilogram. So the way to do that is we just do 1,000 grams divided by 525 grams, and that gives you the conversion to work out how much sodium sulfite is present per kg. Someone's saying, shouldn't you write all your working down? For this question, yes, you should. Although, like, you don't need to write down 30 numbers off your calculator. You can write down like 5 or 6, but just keep the number saved in your calculator. And that should be fine. But yeah, just say don't write out all 30 because that's still a bit of a waste of time. But make sure to keep it on your calculator for accuracy. Let's move on to electrochemistry. I'll answer other questions later. So this is quite a difficult concept to get your head around. But if we look at the center here, this zinc copper cell, this is essentially the way that batteries work. You have 2 electrodes, a zinc, in this case, a zinc one and a copper one. So this is just zinc metal, this is just copper metal, and they're in a solution of their own ions. So zinc is in zinc sulfate, for example, copper is in a solution of copper sulfate. And if you connect both of these electrodes up using wires, and then also something called a salt bridge, which I'll talk about there later. So salt bridge and then wires, it creates a circuit, a complete circuit. What happens when you do this is that one of the electrodes will be a site of reduction and one will be a site of oxidation. We'll get on to how you work out which is which in the next slide, but this is what's happening. So in this case, zinc undergoes oxidation. There is a net conversion of Zn to Zn2 plus. Oppositely, copper undergoes a reduction. There's a net conversion of Cu2 plus to Cu, so like metallic elemental copper. So that means that we have a flow of electrons. Electrons are going to go around the circuit like this, as it shows on the diagram, because the zinc loses electrons, it's oxidized. It loses those electrons to the circuit. Those electrons flow around the circuit and are used to reduce Cu2 plus to copper. So this is how you get electricity. If you put a light bulb there, the electrons would flow through the light bulb and give you a light, so it would light up. So that's just literally how the computer that you're probably watching this on, what is working right now, is that there's a cell in it, a battery. A battery is just the connection of loads of cells doing this to create a flow of electrons. Okay, so that's how a cell works. How would you set one of these up? Well, you'd do it as I've shown you on the left, which is this is how you would draw a diagram of it as well. You have a beaker filled with zinc sulfate, let's say a solution of zinc. You have the zinc electrode, a voltmeter, and then the other electrode. We'll get onto this specific electrode in a second, and you connect it by a salt bridge. A salt bridge is a piece of filter paper or something like that. It doesn't have to be dipped in a solution of ions like potassium nitrate. What that does is it completes the circuit and allows the flow of charge to be complete. Think about it. If there was no salt bridge there, like you just don't have the connection. So it's an open circuit. It's like the switch in a circuit isn't closed, if that makes sense. Why do we use potassium nitrate usually? Well, potassium nitrate, any salt of potassium and any nitrate salt as well are soluble, so it just prevents any solid precipitates forming in the beakers, basically. The reason we use a voltmeter is to measure the voltage, surprisingly, but also it creates a very high resistance if it's in series. Remember that voltmeters essentially have infinite resistance when placed in series. What that does is it prevents the flow of electrons around the circuit. This is quite a confusing concept. So once this voltmeter is in place, no electrons can flow. If it's a light bulb, the electrons can flow, like in this diagram. But if you have a voltmeter, there's no flow of electrons allowed because the voltmeter has infinite resistance. What that means is that the chemical reactions won't actually happen, but they'll be wanting to happen. They'll be like the energy to happen is there. And that's what gives you the voltage reading. It's like putting pressure, but it can't generate those electrons to flow around the circuit. But the electromotive force, the EMF, the voltage, is still there and it wants to push those electrons around, even though it can't. So let's talk about a few more things. The cathode and the anode. This is a way you're going to remember that. A positive red cat. So this is just a picture, the way to remember that. The cathode is always the site of reduction, okay? And the anode is always the site of oxidation. I know some of you might be a bit confused about this because in electrolysis, the cathode is negative and the anode is positive. But if you think about it, in electrolysis and in these cells here, the anode is oxidation, the cathode is reduction. And the reason, and in this case, the cathode is positive in cells, but in electrolysis, as I said, it would be negative. So if you think about it, this makes sense that the cathode is positive and the anode is negative here because electrons are coming from the negative region and are attracted to the positive region. So we talked about that. We talked about the salt bridge, standard conditions. Now, if you want to have your voltage measured to standard conditions so you can compare it to other stuff, there are a couple of things you need to remember. 298 degrees Kelvin. The ion that you're concerned about needs to be at 1 mole per decimeter cubed concentration, and you need to have 100 kilopascals of pressure. So those are your standard conditions. The standard hydrogen electrode. So that's what this is. on the right side of this particular circuit diagram. The standard hydrogen electrode, it's the reference. So you might have come across the concept of a reference before. Like if you do biology, like the colorimeters, how you put like the blank solution in first, it provides something for you to compare everything else against. So the way this works is that you have hydrogen gas come in and react on a platinum electrode. All under standard conditions, you can see it's the ions are at 1 mole per decimeter cube concentration, and that's what this electrode is. And yeah, it's the point of comparison. The reason we use platinum is that there's not obviously you can never get solid hydrogen. It's impossible. It's just physically impossible. So what you want to do is you want to use an inert but like good surface to react on to allow the process to happen. And yeah, that's basically how it all works. Experimentally, if you're doing this in a class, just a key step to remember is to clean all your electrodes with sandpaper and propanone as well, just to wash off all the grease. That gives you better accuracy of results. Also, remember to try and maintain standard conditions. I'm now going to look at some of the questions that people have been asking. Yeah, so why can't the electrons flow when you have the voltmeter? Voltmeters in series have infinite resistance, so electrons just can't pass through that, but they really want to, is what I'm saying. They have the desire to pass through it, but they can't. And that desire gives you the electromotive force. It's like it's like attracted to go through. And another word for electromotive force is voltage. So that's what we do. What is the salt bridge always used? Potassium nitrate solution, aqueous potassium nitrate solution, like a filter paper dipped in that and then used to connect both half cells. We'll get on to what happens if you change standard conditions on the next page. Why do you need a flow of ions via the salt bridge? It completes the circuit and it allows you to balance out the charges that accumulate in the half cells. So that is essentially just completes the circuit. That's all you really need to say. We're going to get on to, yeah, that, yeah, okay. I'm going to explain raw, yeah. So you see this diagram here of the zinc copper cell. They ask you in exams to write a shorthand instead of like spending 10 minutes drawing this out. There's a shorthand way of putting it, which is this, where you have the left hand electrode represented on the left and the right hand electrode represented on the right. The reason I say raw is that you have the reduced version of zinc on the left, the oxidized version of zinc in the middle, the oxidized version of copper in the middle, and then the reduced version of copper on the lateral far side. So that's how you're going to remember that. Is you're going to remember that the anode goes on the left and the cathode on the right, and that you have the reduced versions on the outside and the oxidized versions on the inside. So this is just a shorthand notation instead of drawing out this whole thing. Bear in mind that if you're using like the standard hydrogen electrode and you're using platinum in it, you will need to do a comma at the end where you just do comma platinum PT, just to show that that's what's represented. Yeah, so someone's asking about raw and whether it's whether it's AQA or OCR. Yeah, it's just AQA. It's also EdXL, but not OCR. Let me just read through a couple more questions. Okay, no, we can move on. So what's the purpose of doing what we just did, setting up those electrode systems? Someone that actually before I do that, someone asked how do we use raw? It's just the concept of drawing this out in a shorthand where you have reduced species on the outside and oxidized on the inside. Salt bridge represented by a double line, single line separating each species. Yeah, that's all it is. Okay. I'm gonna move on now and just explain this page before answering any more questions. Basically, if you connect any half cell to the standard hydrogen electrode, because it's the reference point, the voltage that appears on your voltmeter gives you a value known as the standard electrode potential. So for the zinc half cell, it's 0.76 volts. That is the definition, is what I just said. It's the voltage measured when a half cell is connected to the standard hydrogen electrode under standard conditions. So literally in this setup over here, it's under standard conditions. We have the SHE on the right, standard hydrogen electrode, connected to the zinc half cell, and the voltage measured is your standard electrode potential, your E naught value, as some people say. So E naught there. And you'll get given this table in an exam setting, which basically shows you for a bunch of reactions what the E naught standard electrode potential value is. So let's look for zinc. Where's zinc? Zinc is here. So minus 0.76. What does the minus mean? Well, the minus means is that if you connect it to the standard hydrogen electrode, it wants to go backwards. Minus means it wants to go backwards. So from zinc to Zn2 plus 2E. Look at something else. Let's look at copper. Copper has a positive standard electrode potential value, 0.34. So it likes to go forward. So Cu2 plus 2E goes to CuS, copper solid. So those are what that means. The more positive the value is, the more it likes to do this reaction, the more it likes to go in the forward reaction. So fluorine, as you can see, really has a positive, really strong positive standard electrode potential. So it really likes to do this and just react with and get reduced. Remember what I said, something that really likes to get reduced makes an amazing oxidizing agent. So fluorine, very powerful oxidizing agent. Oppositely, very negative standard electrode potentials imply that it wants to go backwards. So lithium really hates to go from Li plus to Li solid. Instead, it really likes to go from Li solid to Li plus because it's a negative value. So lithium really likes to be oxidized, hence it makes a really good reducing agent. So yeah, so now we know the E naughts for particular half reactions, half equations. We want to be able to use that to predict reaction feasibility. The way to do this, let's look at this question to explain how to do this. Use the following equations to predict whether or not Ag plus ions disproportionate in solution. Remember, disproportionation, you're going, it's a single species simultaneously oxidized and reduced. So Ag plus must go to Ags and be reduced, and must also go to Ag2 plus and be oxidized. So the first step when you're predicting feasibility is to write out the equation, the hypothetical equation. So if Ag plus disproportionates, this is what the reaction equation is going to be. Next step is quite simple, actually, is we want to do the E naught for the reduction part of this equation minus the E naught for the oxidation part. And if you do that, that's so the reduction part is this, the one on the left. The oxidation part is this one on the right. So just remember red minus ox, reduction minus oxidation. That's going to be 0.8 minus 2, which gives you minus 1.2 volts. The fact that it's negative implies that this is impossible. This would never actually happen. We've written out a hypothetical equation if it did disproportionate, but the fact that this is negative shows that silver plus will not disproportionate in solution. Just going to mention quickly, just the thing to remember, your whole course relates to each other. All of chemistry is related. So the E cell, the whole voltage of that is proportional to the total entropy change. Therefore, a more positive E cell value implies a more positive entropy change, which, as you might know, means a more likely reaction. It's also more proportional to a more negative Gibbs free energy and proportional to ln K, which is on a couple of your specs, which do with equilibria. So let's look at some of the questions you're asking. Actually, before I do that, just to say, if you change standard conditions, as someone asked earlier, you're going to mess with the values. It won't, the zinc equation, for example, will no longer be minus 0.76. It'll be something else. And therefore your whole maths is going to be interfered with and feasibility really changes. Yeah. And also kinetics, because even if this was feasible, even if it was positive, if it was really kinetically inert, so a really slow reaction, it would basically not happen. Quite a lot of questions in the chat to go through. Uh, would they ask for feasibility in terms of electrode potential for AQA? Yeah, they would. So remember that if your E cell value, which is E reduction minus E oxidation, is positive, that implies energetic feasibility. When okay, let's move on. Okay, because I want to go for a couple of examples as well. Fuel cells, let's just do this quickly. A definition of a fuel cell is when a fuel like hydrogen reacts with oxygen to generate a voltage. And this is one way of generating electricity, and the reactions are shown here. So you can do this acidically or you can do it alkalinely. So let's look at acidic first then. This is the reaction that happens. You pump hydrogen into it. Hydrogen is converted to 2H plus ions and 2 electrons. The 2H plus ions are able to flow through to the cathode where they react with oxygen to generate water. So your product is water and your reactants are hydrogen gas and oxygen gas. Alkaline is similar. Hydrogen pumped into the anode reacts with OH minus ions to generate water, and those OH minus ions are coming from a reaction at the cathode using oxygen. Should you learn those equations off by heart? I would. Like strictly speaking, you don't have to, but it makes it a lot easier if you do. Is that this is what happens in an acidic, this is what happens in an alkaline. There was one spec actually where I think they said that you'll never get assessed on it. I think it was OCR, but I'll double check that at the end. But like as you can see, this is the AQA one here. You do need to know AQA. You don't need to know acidic, the acidic fuel. So you do need to know alkaline, but you do need to know those reactions. It's probably easiest to do that off by heart. Notice that both of them produce water as a product as well. So that's good, obviously. Think about other fuels that you've come across, like burning like octane in petrol in cars, produces carbon dioxide and carbon monoxide, pollutants. If water is your only product, that's a good fuel. So that's an advantage of it. It's also quite an efficient way of generating electricity. You could generate energy if you burnt hydrogen, but it's just less effective. It also can be renewable. Hydrogen is produced on an industrial scale by the electrolysis of water. So if you're able to do that electrolysis using like wind power, then yeah, it'll be renewable. But if you're using, I don't know, like oil, petrol to generate that energy, it's not going to be renewable. Disadvantages of fuel cells, though, are that the hydrogen is hard to store and that the cell has a limited lifespan as well. It's really expensive to do. Another thing I need to mention is that that's one way you can generate electricity on like an industrial scale. Another way is just a standard cell. So as you saw here, like my computer battery, for example, basically works on this principle over here with the zinc and the copper. There's no voltmeter in place allowing electrons to flow. Those electrons flow through a circuit and generate the lights on my computer, all of those different things that my computer is doing. Disadvantage of this, and the reason you might want to put a voltmeter in there if you're doing this in a lab, is that eventually the whole of my zinc electrode is going to turn into zinc ions. So eventually you won't have an electrode left here. It just degrades into ions. And so that at that point, the battery dies, the battery is dead. no more electrons can flow around the circuit. How do we remedy that? Well, we charge your computer, don't we? When I put my plug into my computer to charge it, I'm sending electrons into the circuit to rebuild this electrode over here. Now, in my computer, it's not actually a zinc copper system. It works in the same way. It's just you're not using zinc and copper specifically. Instead, you're using this lithium setup where your cathode has this reaction, your anode has this reaction, and then the electrons drive the generation of electricity for my computer. We don't really have much time to go through all of these questions, so ignore the stuff on the right-hand side of this page. State the substances and conditions needed in a standard hydrogen electrode. I'll just say quickly, 298 Kelvin conditions, 100 kilopascals, and that means the hydrogen gas must be at 100 kilopascals too. And then acids, H plus ions at 1 mole per decimeter cubed concentration. Ignore the stuff on the right-hand side. That would take too long. Yeah, there you go. Let me just look at questions. Are the yeah, the pros and cons about the fuel cells apply to both acidic and alkaline fuel cells. As I said, they're essentially the same thing, except they have different chemical reactions. Okay, let's look at some more questions that people are asking. I'm just gonna, people are asking, so people are asking me to just explain the fuel cell in a bit more depth. Basically, let's look at acidic. What we're doing is the same as with the zinc and the copper, but it's just different chemicals and different reaction. Hydrogen is coming in, and at the anode, it is oxidized to this in this reaction, loses electrons. The electrons flow around the circuit, giving energy to my computer, let's say, even though it's not actually in my computer, but it could be. And those electrons flow around the circuit and they're used for the reduction reaction at the cathode to generate water. Alkaline is the same thing, just different sets of reactions. So they're basically a way of generating electricity in a fairly renewable, clean way, is the takeaway for that. And as I said, as it says here, fuel cells use reaction of a fuel like hydrogen with oxygen to generate a voltage. Let me just see. Any more questions? Manganate titration, what's the color change? Colorless to pale pink. Yeah, I think you get access to the Zoom and the PowerPoint after the lesson. How do you recharge a fuel cell? You just add more hydrogen into it. You just get another bottle of hydrogen and plug it in, which is actually really expensive and hard to do because, as you can imagine, it's a really flammable gas. So it's just a bit like difficult to do. Does hydrogen go to the computer too? It doesn't in the case of my computer or really anyone's computer, but hypothetically it could because it's a way of generating electricity. How does changing conditions affect electromagnetic the driving force? It's basically it just someone said on the chat earlier, it's due with like Le Chatelier's principle. But like if we look at the zinc reaction, Zn2 plus 2E minus goes to Zn. We know that usually it's going to run in the oxidation direction, going from zinc to Zn2 plus. But if I was to increase the concentration of Zn2 plus ions in my solution, according to Le Chatelier's principle, the equilibrium is going to be shifted to the right, which is going to make this value, the E naught for this reaction, more positive, and that's going to have mathematical effects on the E cell calculated, making the reaction more or less feasible. What equations should we learn for commercial uses? For AQA, just learn the alkaline one. So do two equations here. And then Edexcel, you want to learn both. And OCR also, I think you want to learn both. Although technically you don't have to memorize them, but like it's just really helpful if you do. Save some time in the exam having to work them out. Just to clarify, hydrogen ions are formed in the reaction at the anode in the acidic one, and then they diffuse over to the cathode for reaction with oxygen. The electrons can't move like this though. So the electrons are forced around an external circuit to generate electricity. Uh, yeah, okay. Yeah, the looking at just I'm answering questions now, by the way, just to clarify, but uh yeah, so the in terms of standard electrode potentials, the more negative one is going to be the oxidation one. So in the zinc copper reaction we saw earlier, this is going to be the more positive copper one is going to be reduction, copper 2 plus to copper. The more negative zinc one is going to be zinc to Zn2 plus. We want to look at a couple more maybe one more question. Just before we go. This last thing before I turn off Zoom meeting, I just want to go through it because it's quite important. It's just a way for you to have a go at calculating feasibility. So just read this question, have a think about it, and then in 30 seconds, I'll go through it and explain it. This could be OCR at Excel2, so everyone should have a go at this. Okay, so why does copper not usually react with acid but reacts with nitric acid? Well, if you look at the fuel cell, if you look at the, sorry, I don't know why I said that. If you look at the E naught values, copper usually likes, it's positive. So likes to go from Cu2 plus to Cu. So it likes to go forward. And if you react it with any acid, the acid is H plus ions that like to form H2 gas. So that also likes to go forward. And you can't have both going forward. That's two reduction reactions. It's impossible. So if that hypothetically did occur, you'd have a negative E cell value. But in nitric acid, the copper reacts with nitrate, not the H plus ions, and your E cell value is positive. It's, was that 0.62, I think, plus 0.62. Positive E cell value indicates feasibility. Yes, that's what this says. Just a couple more things to say. In terms of someone wants me to explain the alkaline fuel cell better. Okay, I will. Hydrogen comes into the anode. Actually, I'll start with the cathode this time. It makes it easier. You have oxygen pumped into the cathode, where it reacts with water via reduction reaction to form alkaline OH minus ions. Those OH minus ions can diffuse to the other side where the anode is, react with hydrogen gas to generate water, your product. Electrons can't diffuse through though and have to go around an external circuit. Hence, you get electricity. Also, just to clarify, when I say it can be renewable, but it's not necessarily renewable, I says that this is because the hydrogen gas you have is generated by the electrolysis of water. To power the electrolysis of water, you could use something renewable like wind power, hence it would be renewable, or you could like burn petrol or something, and that would be non-renewable. Okay. Uh, yeah, I'm going to go back to the marking for the copper question. There, yeah, I have another question on here actually that we can go through as well about fuel cells, just to look at what the exam boards like to ask. But just if someone else they wanted to see this mark scheme page again, there you go. I'll just keep on for a couple more seconds, and we'll just end the session by looking at the OCR question, which is on fuel cells. Okay, OCR. So just have a look at these questions and think about how you would go about solving them. Okay, that should be enough time. This one on the left, you basically, as I said, you could have just memorized those equations, but if you hadn't, you can still work them out. Anything that's involved in the acidic fuel cell is going to have H plus, so like the second one and the fourth one. Anything involved in the alkali fuel cell is going to have OH minus, so like the first and the third one. And you can work out which is the reduction, which is the oxidation using the E naught values. So reduction is going to be the more positive one. And if you put those equations together, you'll see that both fuel cells have a E cell value of positive 1.23. So that explains how they're both able to work and function. And they also they have the same overall equation if you combine them. And you'll see that's how it works, which is that they produce water, oxygen and hydrogen reacting to produce water. Let's look at the right hand side now. So fuel cells and storage cells. Just a fuel cell involves the reaction with oxygen. So it's about gases being pumped in. Storage cells are like they're like that what we showed earlier with like the zinc and the copper. Why is ethanol better than hydrogen? It's less flammable. So remember what I said, the disadvantages of using hydrogen are it's expensive, it's flammable, it's hard to store, etc. So this is just an organic chemistry question, which is what the reaction is when you combust ethanol. Deduce the half equation for the reaction of at the oxygen electrodes in this. Well, it's just going to be the equation. I think it's the fourth one over here. It's just the concept of the the electrons going around the circuit and then reacting with the oxygen to produce the water, like it is here. And then this one's just AS level redox. Let's look at the mark scheme. So yeah, this is the acidic one, alkaline, and both positive 1.23. Fuel reacts with oxygen in a fuel cell, as I said. Ethanol is a liquid, easier to store. This is the combustion equation. That's the equation there. And then you just use the oxidation states to look at what's oxidized, what's reduced. And that's basically everything. I'm just going to answer a few more questions before. Yeah, I think there's not really any more questions in the chat. All right, here actually is one. How do you know when to use the hydrogen cell and when to use electrodes? Use the hydrogen cell when you want to when you want to find the standard electrode potentials for all the other cells, like the zinc or copper one. So it's a way of measuring stuff. Oh wait, sorry, I misread. Okay, yeah, sorry, I read that wrong. That when to use the hydrogen fuel cell versus when to use like storage cells like the lithium one. Well, it's up to you, but I would think that the lithium one is just easier to use. It's just very easy to put in a computer. Whereas if you had the hydrogen in your computer, firstly, that's really dangerous because the hydrogen could just explode, and secondly, that's just like really inconvenient because you'd have to have like a whole bottle of hydrogen being refilled all the time. But it works well in like some cars that they're designing, I think, just because you can just fill it up with hydrogen. So it's not really used that often, even though it does work. Someone said about purple to colors, color change. Yeah, so that's when you switch over the flasks, basically. You don't, it's up to you what goes in the burette, what goes in the conical flask. You don't have to memorize the fuel cell equations, but you can if you want to because it makes it faster. Otherwise, you could just calculate them in the exam. If the electrons can't go through the circuit, how do they move between the electrodes? Uh, when the voltmeter is connected, they don't. They just really want to, as I said before. It's like they're attracted to the other side, but the voltmeter is stopping them. And that's what the voltmeter picks up on. That's what the voltage is. If there was no voltmeter and the circuit was connected, the electrons can just flow through the wires. Uh, okay. I'm just gonna end. Last question is just about the last question I'm going to answer is in the alkaline fuel cell, can you write the equations? Okay, let's have a look. Uh, yeah, so it's actually the easier way to show this is on the here for the alkaline fuel cell. It's the wherever the OH minuses are, so number one and number three. And when oxygen is pumped in to the cathode, it gets reduced and reacts with water and forms the hydroxide ions. And then those move through to the anode, react with hydrogen gas that's been pumped in to form water. And that flow of electrons around the circuit is what gives you electricity. I think that's enough for today. Uh, yeah, I'm pretty sure that's everything. Unless I'll give like 10 more seconds for people to write any really urgent messages. Uh, Otherwise, I'm going to end the meeting there. No problem, guys. Thank you for coming. I don't know if you'll have me next time. I don't know who it will be. But yeah, that's basically it. I'm going to end the meeting now, everyone, then. Thank you for coming and good luck.